Every day, millions of barrels of crude oil arrive at one of the largest and most complex industrial facilities ever built. Stretching across an area larger than many cities, the world's largest oil refinery never truly sleeps. It operates 24 hours a day, 7 days a week, transforming raw crude oil into gasoline, diesel, jet fuel, liquefied petroleum gas, lubricants, petrochemical feedstocks, and dozens of other products that power modern civilization. From space, these refineries appear like enormous industrial cities filled with thousands of pipelines, towering distillation columns, massive storage tanks, and countless processing units. Although they may look overwhelming from the outside, every pipe, valve, pump, and control system has a specific purpose. Together, they form one of the most sophisticated manufacturing systems ever created by human engineering. An oil refinery is far more than a collection of machines. It is a carefully designed industrial ecosystem where chemistry, physics, mechanical engineering, automation, and logistics work together with extraordinary precision. Every minute, thousands of different processes occur simultaneously. While one unit is separating crude oil into different fractions, another is converting heavy hydrocarbons into lighter fuels, another is removing impurities, and yet another is preparing finished products for shipment. Despite the incredible complexity, every process is coordinated through advanced computer systems that monitor the refinery every second of the day. The journey begins long before crude oil enters the refinery. Oil extracted from wells around the world is transported through pipelines, supertankers, rail cars, and tanker trucks until it reaches the refinery's enormous storage terminal. Some of the world's largest refineries receive crude oil from multiple countries at the same time, processing different grades of petroleum depending on market demand. Before unloading begins, laboratory technicians carefully analyze every shipment to determine its density, sulfur content, chemical composition, and overall quality. This information allows engineers to decide exactly how each batch should be processed for maximum efficiency and product yield. After inspection, the crude oil is pumped into gigantic storage tanks that dominate the refinery landscape. Many of these tanks are taller than multi-story buildings and can store millions of liters of petroleum. Floating roof systems move up and down with the oil level, reducing evaporation losses while improving safety. Thousands of electronic sensors continuously monitor liquid levels, temperature, pressure, and vapor emissions, allowing operators to supervise every tank from centralized control rooms without needing constant manual inspection. Before refining begins, the crude oil passes through desalting units where salt, sand, dirt, and water are removed. Although these impurities may seem insignificant, even small amounts of salt can cause severe corrosion inside expensive refinery equipment operating at extremely high temperatures. Water is mixed with the crude oil, dissolving the salt before powerful electrical separators remove the contaminated water. This cleaning stage protects downstream equipment while improving both efficiency and reliability throughout the refining process. The clean crude oil then enters a network of heat exchangers that recover energy from other refinery operations. Instead of wasting heat already produced elsewhere in the plant, engineers use it to preheat the incoming crude oil, dramatically reducing fuel consumption. After passing through these heat recovery systems, the oil enters enormous furnaces where temperatures approach 400 degrees Celsius. At this point, much of the crude oil vaporizes, creating the ideal conditions for the refinery's most important operation. The heated mixture flows into the atmospheric distillation tower, one of the tallest structures inside the refinery. Some distillation columns rise higher than a 20-story building and contain dozens of internal trays where separation takes place. As hot vapor travels upward through the tower, temperatures gradually decrease. Heavy hydrocarbons condense first, while lighter hydrocarbons continue rising before condensing higher inside the column. This remarkably efficient process separates crude oil into gases, naphtha, kerosene, diesel, gas oil, and heavy residues based entirely on their different boiling points. However, distillation only performs the first stage of refining. Many of the separated fractions still require additional processing before becoming usable fuels. Heavy oils are transported to catalytic cracking units where enormous hydrocarbon molecules are broken into smaller, more valuable products. Inside these reactors, Finely powdered catalysts accelerate chemical reactions that increase gasoline production while maximizing the value of every barrel of crude oil. Without catalytic cracking, modern refineries would produce far less transportation fuel than today's global economy demands. Another essential processing unit is the hydrocracker. Operating under extremely high temperatures and pressures, hydrocrackers combine hydrogen with heavy petroleum fractions to create cleaner diesel fuel, aviation fuel, and premium gasoline components. At the same time, sulfur and other impurities are removed, helping produce cleaner burning fuels that comply with increasingly strict environmental regulations around the world. Catalytic reforming is another critical stage inside the refinery. Rather than increasing fuel quantity, this process improves fuel quality by rearranging hydrocarbon molecules into structures with much higher octane ratings. High-octane gasoline allows modern engines to deliver better performance while reducing engine knocking. Reforming units also generate large quantities of hydrogen gas, which is reused throughout the refinery in other purification processes, improving overall efficiency while reducing waste. Hydrotreating units operate continuously to remove sulfur, nitrogen, oxygen compounds, and trace metals from petroleum products. Hydrogen reacts with these unwanted contaminants over specialized catalysts, producing cleaner fuels that release fewer harmful emissions during combustion. Without hydrotreating, modern low-sulfur gasoline, diesel fuel, and jet fuel would not meet international environmental standards. This process has become one of the most important operations inside every major refinery. Hidden beneath the towering processing units is an incredible network of pipelines. The world's largest refineries contain thousands of kilometers of interconnected pipes carrying crude oil, steam, cooling water, hydrogen, natural gas, compressed air, chemicals, and finished petroleum products between different processing units. Every pipeline is carefully designed to withstand extreme temperatures, high pressures, and corrosive environments while operating continuously throughout the year. Color-coded markings, automated valves, and sophisticated monitoring systems help operators manage this enormous industrial network safely. Moving these enormous volumes of fluids requires equally impressive pumping systems. Hundreds of industrial pumps operate simultaneously, transporting millions of liters of liquids every hour through the refinery. Massive compressors handle natural gas and hydrogen, while giant cooling towers remove excess heat generated during refining. Large boilers produce high-pressure steam, used throughout the facility for heating, power generation, and process control. Every utility system must operate flawlessly, because even a brief interruption could affect production across multiple refinery units. Electricity distribution inside a giant refinery resembles the power network of a small city. Dedicated substations receive high-voltage electricity before transformers reduce it to the appropriate levels required by different equipment. Thousands of electric motors drive pumps, compressors, fans, conveyors, mixers, and countless other machines. Backup generators and emergency power systems ensure that critical operations continue even during unexpected power failures, protecting both personnel and valuable equipment. The heart of the refinery is not located among the towering processing units, but inside the central control room. This highly secure operations center contains enormous digital displays showing every major process taking place across the facility. Thousands of sensors installed throughout the refinery continuously measure temperature, pressure, flow rates, liquid levels, chemical composition, vibration, and equipment performance. Engineers monitor this information in real time, allowing them to detect even the smallest changes before they become serious operational problems. Artificial intelligence and advanced automation now play an increasingly important role in refinery operations. Machine learning algorithms analyze millions of data points every day to optimize fuel production, reduce energy consumption, predict equipment failures, and improve maintenance schedules. Digital twin technology even allows engineers to simulate entire refinery operations using virtual computer models before implementing changes in the real facility, reducing both costs and operational risks. Safety remains the highest priority because refineries process enormous quantities of flammable materials under extreme temperatures and pressures. Fire detection systems, gas monitoring sensors, emergency shutdown valves, water deluge systems, foam suppression equipment, explosion-resistant electrical installations, and multiple backup safety systems operate continuously to protect workers and equipment. Every employee receives extensive safety training, while emergency response teams conduct regular drills to prepare for unlikely but potentially serious situations. Environmental protection has also become a central focus of modern refinery design. Advanced wastewater treatment plants clean millions of liters of industrial water before it is reused or safely discharged. Sulfur recovery units capture sulfur compounds that would otherwise contribute to air pollution, converting them into valuable industrial products. Waste heat recovery systems improve energy efficiency, while carbon reduction technologies continue to reduce greenhouse gas emissions. Many refineries are also exploring renewable hydrogen, carbon capture systems, and biofuel integration as part of the transition toward cleaner energy production. After refining is complete, every fuel undergoes extensive laboratory testing to verify its quality. Scientists analyze octane ratings, sulfur levels, flash points, viscosity, density, freezing points, and numerous other characteristics before approving products for distribution. Finished fuels are stored inside massive tank farms before being transported through pipelines, tanker ships, railway tank cars, and road tankers to airports, fuel terminals, industries, and service stations around the world. Some of the world's largest oil refineries process well over 1 million barrels of crude oil every single day. To achieve this extraordinary level of production, they rely on tens of thousands of instruments, hundreds of processing units, thousands of workers, and millions of individual engineering components, operating together with remarkable precision. Every hour, these industrial giants transform raw petroleum into the fuels and materials that support transportation, healthcare, manufacturing, agriculture, aviation, and countless other industries that modern society depends upon. Although most people never see the inside of a refinery, these enormous industrial complexes quietly keep the modern world moving. Through advanced chemistry, powerful machinery, intelligent automation, and decades of engineering innovation, they transform one of Earth's most valuable natural resources into dozens of essential products used every day by billions of people. From the moment crude oil enters the refinery until the finished fuels leave for destinations around the globe, every stage reflects one of humanity's greatest achievements in industrial engineering, proving that behind every drop of fuel lies an extraordinary world of science, precision, and technology.